Okay, the next few pages are revision, really, with just a few new words thrown in there. But generally, everything on the next few pages you should be able to do already. So feel free to just whiz through them yourselves and then just come back and check that you've got the correct answers. But if you want to just follow through with me, that's fine too, just for a revision exercise. So electric circuits. So electromotive force, EMF. EMF is basically what you've just been calling voltage up until now. So electromotive force is the energy given to each coulomb of charge by a source of electrical energy. So the source of electrical energy, so like a battery or something, has a certain amount of voltage. And the EMF is and the voltage is the energy given to each coulomb of charge. The EMF is the energy given to each coulomb of charge by a source of electrical energy. For example, the EMF of a cell is the number of joules of energy given to each coulomb of charge by the chemical reaction within the cell. It's measured in volts, and an EMF of 1 volt means that each coulomb of charge requires 1 joule of energy. So just what you've been calling volts up until now, it's just a new sort of name to replace it. So if a cell is connected across a resistor, a current will flow. So we've got a cell here with an EMF of E volts, and the cell gives E joules of energy to each coulomb of charge passing through the cell. And the resistor here, because it's just one resistor in series with one cell, the resistor will get all of that voltage. So each coulomb of charge has E joules of energy available to transform into heat in the resistor. And we know that the more resistors you have in circuits, the voltage is shared in a series circuit. But if you just got one resistor, it gets the entirety of the EMF supplied by the cell. So the rate at which charge flows through the circuit is called current. Current is measured in units called amps, capital A, or coulombs per second, which is absolutely fine, but capital A is probably easier. So current is the voltage divided by resistance. And in this ideal case, and in the next booklet you'll see this, sometimes it's not always ideal. The current is that EMF, E volts, divided by the resistance of the resistor. Because we're assuming that all the energy available from the source is transformed into heat energy in the resistor. And the rate at which the energy is transformed into heat in the resistor is called power, and P equals IV. Power is current times voltage. So these equations you've already come across before. And in the ideal case, power is the current times by the EMF, the voltage there, E. So just a reminder about your resistors in series. So if you've got R1, R2, and R3 in series, then the total voltage, the EMF, is split between the resistors. So voltage 1 would be the current times by R1, voltage 2 would be the current times by R2, voltage 3 would be the current times by R3. If you know the current and you know the resistance, you can work out the voltage through each one. You could also say that there's an equivalent big resistor, which is the equivalent of all three of those resistors together, and the equivalent voltage across that resistor is the current times by the equivalent resistance of all the resistors together. So Req replaces R1, R2, and R3. So it's the total resistance in the circuit. So the voltage, which should be E, would be I times by the equivalent resistor. So we know in a series circuit, the EMF is the sum of the potential differences. So V1 plus V2 plus V3 is equal to the total voltage, which in this case we've called capital E. So replacing V1 by IR1, V2 by IR2, and V3 by IR3, we can say that the EMF, the total voltage, is IR1 plus IR2 plus IR3. We also know from this circuit here, the equivalent resistance and the equivalent voltage, that the E, total voltage, is the same as the voltage across that equivalent resistor. So E equals VEQ. So replacing VEQ by IREQ, so current times by the equivalent resistance of all of them. So the total EMF is equal to I times R equivalent. But also, we just said earlier that the total EMF is also equal to IR1 plus IR2 plus IR3. So because I is the same in a series circuit, we can cancel the I's out and we end up with the equation that we know and love. R1 plus R2 plus R3 is the equivalent resistor. So the total resistance in a series circuit is R1 plus R2 plus R3. All you need to know is the outcome there. To find the total resistance in a series circuit, you add the resistors up, which you know from National 5 already. So, some information about the circuit below has been provided. Complete the missing information. So you've got missing current, missing EMF, so total voltage, and you've got some missing voltages. You've also got some missing energy per coulomb, which is the same as the voltage. So I'm sure you can do this yourselves. I will walk you through it, but feel free to pause the video and just do it yourself if you prefer to do that. So what I'm going to look at first of all is I'm going to look at this part here because that's going to give us a lot of information there. So because we know the current is the same at all points, the current through the 4 ohm resistor is the same as the current through the 8 ohm resistor is the same as the current through the 12 ohm resistor. So first of all, find the current. Using the 4 ohm resistor. So we know that current is the voltage over the resistance. So the voltage of the 4 ohm resistor is 2. The resistance of the 4 ohm resistor is 4. So the current is 0.5 amps. So we've got 0.5 amps there. So that's as we know the current. And now, because we know the current and we know the resistances, we can find the voltage across each one of the resistors. So find voltage across 8 ohm and 12 ohm resistors. And to do that, we just do V equals IR. So the voltage across the 8 ohm is 0.5 times 8, which is 4 volts. And the voltage across the 12 ohm is 0.5 times by 12, which is 6 volts. So we've got these ones now. So we've got 4 and 6. So it's 4 joules of energy and 6 joules of energy. Total joules of energy per coulomb, you add them all up together. So 6 plus 4 plus 2 is 12. And to find the EMF, it's just the total voltage. So it's V1 plus V2 plus V3, which is 2 plus 4 plus 6, which is 12 volts. Okay, the next one is resistors in parallel. So again, here's the proof of it. You don't need to know the proof, but it's just for interest. But you do need to know the rule. So consider 3 resistors, R1, R2, and R3 in parallel. So we've got the same kind of thing here again. So we've got an equivalent resistor, which is a combination of all 3 of them. We've got R1, R2, and R3. And we know that the current splits up. So the current, this is your total current, and then some of it goes down that. The rest of it carries on along here. Then some of it goes along this branch. The rest of it carries along there. So the total charge in 1 second, the current flowing through R1, R2, and R3 must equal the charge supplied by the cell. So the total current is I1 plus I2 plus I3. And we know that the current is V divided by R, and we know that the voltage is the same across each branch. So each branch we'll get the same and the same as the supply voltage, which is E in this case. So I equals I1, which is V over R1, so E over R1. I2 is E over R2, and I3 is E over R3. But if you look at the equivalents here, then the current is just the voltage divided by the resistance, so E over Req. So we've got E over R1 plus E over R2 plus E over R3 is equal to E over the equivalent resistor. And again, E is the same at all points, so we can cancel E out, and we end up with 1 over R1 plus 1 over R2 plus 1 over R3 is 1 over the equivalent resistor. So that's the outcome that you need to know, that you do know from National 5 anyway. So another example, again, you should be able to do this. Feel free to pause it, have a go, and then just check your answers with me afterwards. But I'm just going to go through it and walk you through it. So we've got a few missing pieces of information again there. We have got one nice part of information here, which we can sort of gain quite a lot of information from in the start. So first thing we need to do, find the potential difference across that 4.5 ohm resistor. So PD across 4.5 ohm resistor. So to do that, V equals I times R. So we've got the current and the resistor there. So 2 times 4.5, which is 9 volts. So we've got 9 volts along there. That must mean we've got 9 volts along there, which also means we've got 9 volts along there. And our EMF, our total voltage, is 9 volts. Okay, what else do we need? We need the current through the 18 ohm resistor. So current through 18 ohm resistor. So to do that, it's I equals V over R. We know the voltage now is 9 and the resistance is 18. So it's 0.5 amps. Then we've got a final resistor. So find the final resistor. So R equals V over I. Voltage is 9 because it's the same across each branch, divided by the current in the resistor through that resistance, which is 3. So 9 divided by 3 is 3 ohms. And then we need to find the total current. So we just need to add them up. So 2 plus 0.5 plus 3, which is 5.5 amps. So that was 0.5, and that's 5.5 amps. Okay, I'm going to leave you to do this one, and then I will give you the solutions to check afterwards.